Hello, hi to everyone. Welcome back to our channel. Now we are moving to the lecture number 3 from series AC circuit, that is a unit 2 chapter number 2. Okay, with that we are going to complete the chapter number 2 series AC circuit. So the concept here, still now we discuss RL and RC circuit. Now we are moving to the RLC circuits. What exactly the RLC circuit phasor diagram and then remaining related formulas. So in case of RLC circuit, series circuits especially, resistor, inductor and capacitors are connected in series. Here, the voltage drop across a resistor will be, all are connected in series, right? So all are connected in series, current is I only. So I into, so here, current will be the same in case of series circuit. The voltage drop across a resistor is IR. You know that resistor voltage and current are in phase. Voltage and current are in phase. That is the first case you need to remember. After that, inductor. Inductor is a VL. XL is the inductive reactance. Just now we explained in the previous lecture. So it is product is I into XL is a voltage drop. In this particular case, I am taking the current as a reference. I am taking as a current as a reference. Voltage and current are leading by 90 degrees. So leading by 90 degrees. Which one is the leading? Current. Current is leading by 90 degrees. In this particular case, I am taking the current as a reference. So in this particular phasor diagram. So VC, voltage across a capacitor I into XC. So here voltage and current lagging. Which one is a lagging here? Voltage is a lagging by 90 degrees. Is it okay? So now we are moving to the phasor diagrams. Look at here. So how exactly the phasor diagrams will be? We have two cases or possible cases. The first case, in case of XL is greater than XC. Second case, XC is greater than XL. These two cases we have two phasor diagrams. For example, XL value is a more. The first case, look at here. This is a voltage VC, voltage across a capacitor. This is a voltage across a inductor. The subtraction whenever XL is more, so once we subtracted both XL minus XC, the quantity is a positive only. Now here the phasor sum of Pythagoras, we can apply the Pythagoras. I will directly write the equation. V is equal to square root of, this particular diagram is converted into impedance diagram. So Z and then XL minus XC. This is a XC. So I is common for everything. So that's why we can take I into R square plus I into XL minus XC. Here XL value is greater than XC. Okay. So I is a common. So finally we have a R square plus XL minus XC whole square. So I can take this particular I in the right hand side. I will get V by I is equal to square root of R square plus XL minus XC whole square. So finally you need to remember what is the formula for Z? Impedance R square plus XL minus XC whole square. You got the same thing. Z is equal to Pythagoras R square plus XL minus XC whole square. That is about the impedance formula we have to remember. In the examination point of view, we have to remember this particular formula. For XL is greater than XC for series RLC circuit. If it is a second case, what is the second case? We have Z value XC is greater than XL. Okay, XC is greater than XL. So square root of R square plus XC minus XL whole square you will get. That is a formula for impedance whenever XC is greater than XL. So XC is dominating that. So this is about the series RLC circuit. In the same phasor diagram, we will get this total complete portion will get here XC minus XL in that particular case. Okay, right. Next we are moving to the resonance in RLC circuit. So the resonance in RLC circuit, whenever resonance occur, whenever capacitive reactance is equal to inductive reactance, whenever this particular condition is occurred, then you will get the resonance frequency. The resonance directly I will give the formula, because we are attending the competitive exam, derivation is not required. Whenever it is required, I will explain. So directly I will tell you the concept behind that. So resonance in RLC circuit. In case so XL is equal to XC. Whenever XL is equal to XC, we have a already Z is equal to square root of R square plus XL minus XC or XC minus XL. Whenever this condition is applied to that, then you will get both are get cancelled. You will get R. So that means that whenever resonance occur, whenever XC is equal to XC, resonance will be occur. Whenever resonance occur, impedance Z is equal to R. So impedance is equal to only resistance. Whenever Z is equal to R, what about the power factor for formula, from the lecture number 1 and 2, power factor formula cos phi is equal to R by Z. Otherwise, from the phasor diagram, from this phasor diagram, we can tell you that power factor cos phi is equal to opposite divided adjacent divided by hypotenuse. What is the adjacent value? R. Hypotenuse is a Z. Okay, so cos phi is equal to R by Z. R and Z are same, then you will get the 1. That means that you need to remember another thing. Every point is important in the examination. Whenever resonance occur in the RLC series circuit, the impedance is equal to resistance as well as power factor is a unity. So after that, XL is nothing but a 2 pi FL. Yes or no? XC is nothing but a 1 by 2 pi FC. So from that, F square is equal to 1 by 2 pi square F square CL. So finally F is equal to, that means that F at resonance frequency is equal to 1 by 2 pi, there is no F here, 1 by 2 pi root LC. This is a formula for resonance. So this formula is important for the examination. So everyone note down this particular formula. F naught is equal to 1 by 2 pi root LC. So you got the idea about the resonance frequency. Now resonance frequency, the formula I further simplify, 1 by 2 pi is nothing but a 0.159 divided by root LC. That is also approximately equivalent to 0.159 is nothing but 0.16 by root LC. Maybe in the examination this particular formula is also mentioned directly, so don't waste your calculating the time to 1 by 2 pi value is a 0.159 or 0.16. Directly I provided you. So this is about the resonance in RLC series circuit. Now we are moving to the resonance curve. Okay, so what exactly the resonance curve? The one more point here I would like to mention, at resonance condition, current value I is equal to V by, actually current I is equal to V by Z. Whenever Z is equal to R, so finally IM, current will be, IM is equal to, current will be maximum at resonance, V by R. This is the current at resonance. You will get the maximum current at resonance condition, because the impedance value, the reactance value is going to be 0, impedance value going to be decreases. What about the current value going to be increases? That's why it is a magnifying circuit. The resonance circuit here also call it as a current magnifying circuit. Current magnified circuit. Clear? Next we are moving to the resonance curve. So resonance curve, look at here, the curve in between frequency versus current. So now my question here, the resonance curve for different resistances. Look at here, I maximum is equal to, just now I given V by R. So what I am saying that whenever I use the resistance value is very less, for example, what about the current value very high, that means that we are decreasing the resistance. What about the current value of peak value increases, that means the sharpness is more whenever resistance is very small. For example, resistance will be medium, the curve will be also sharpness is medium. Whenever resistance is increases more and more very high, what about the current is decreases. So see here, the this particular curve, okay, current resistance is very high, what about the current value very less. This is a flattened curve. So this what the resonance curve effect related to the resistance. In the examination, it is a chances there, the sharpness of curve is increases, our resonance curve is a very sharpness when our resistance values are very small. Okay, next we are further moving to the characteristics of series resonance circuit. Just now I gave the characteristics one by one, will recall it. Just now I gave the complete details related to the resonance RLC derivation and everything. From that we are going to discuss. The first point here, the current in the circuit is maximum. At resonance, current in circuit is maximum. Okay, that is the first point you need to remember, that maximum current is Im is equal to V by R. Okay, right. Next one, the circuit offers minimum impedance. So Z minimum, it offers very minimum impedance, Z is equal to R. So at resonance, XL is equal to XC, both XL and XC get cancelled. That means that the resultant value of the impedance is decreases. That is the third point you need to remember. The fourth point you need to remember, circuit behaves like a pure resistor. Circuit behave like a pure resistor. Whenever it is behave like a pure resistance circuit, what about the power factor cos phi is unity. Very important. They will you can expect the one question they will give in the examination. At resonance condition, the power factor of the circuit, they will provide unity power factor 0.5, 0.7 or 0.9 and none of the above, for example. So power factor is unity, you need to choose that. Next one, you know, V and C, the maximum, they are magnitudinally equal, cancel with each other out of phase. That means that XL and XC are both are opposite in the phasor. So that means that V and VC both are equal but opposite phase. Okay. So next, the last point, at resonance frequency F naught is equal to, the formula will be 0.159 by root LC or 0.16 root LC. So this is about the resonance frequency, the main characteristics. Then we are moving to the bandwidth of tuned circuit. So it is a bandwidth of tuned circuit. I will select the one frequency curve. So this is a resonance frequency curve. At what frequency resonance occur? This is a F naught. The maximum current will occur. That is a resonance frequency. Now the bandwidth is nothing but at the half of the current, half of this maximum current, at the middle of the what we call at the middle of the graph, this particular resonance curve, you will get the current of 1 by root 2. That means that 0.707 times of current of the maximum current. You will get the two frequencies, F1 and F2. At that particular frequencies, you will get half power. What we call half power. That means that the power output of the circuit, you will get the half of the power from the total entire circuit. That particular frequencies you are call it as a upper cutoff frequency and lower cutoff frequency. So we have a F1 is a upper cutoff frequency and F2 is nothing but a lower cutoff frequency. Right. So in this all these cases, upper cutoff and lower cutoff frequency, the bandwidth is a difference of both. F1 minus F2 is equal to F1 minus F2 is nothing but a bandwidth that will be equivalent to 2 by RL. So everyone remember this particular formula, F1 minus F2 is equal to R by 2L. So F1 minus F2 is nothing but a bandwidth that will be equivalent to, F0 divided by Q. How you will get F0 divided by Q? So based on this particular equation, we are going to derive that F0 is equal to 1 by root LC. We are substituting everything, you will get this particular formula. But in the examination, we have to remember both the formulas issued. So I am not providing the derivation here. Okay. What is important for the examination point of view, I will provide it. Because very less time is there. Only today is the February 1st. Only 10 days in your hand. So everyone be focused and then prepare. Okay. After that, half power frequency formulas I will going to give you. What is half power frequency? F1, that is our upper cutoff frequency. That formula will be F0 into delta F by 2. So that will be equivalent to F0 minus bandwidth divided by 2. That will be also equivalent to F0 minus R by 4 pi L. This is the formula. Next, F2, lower cutoff frequency, F0 minus delta F by 2 plus F0 plus bandwidth divided by 2, F0 plus R by 4 L. These are the formulas we have to remember. Okay. Then we are moving to the next topic, that is a sharpness of resonance curve. Sharpness of resonance curve. In the sharpness of resonance curve, whenever resistance is a very large resistance, this is a curve we will get. Okay, just now we discussed about the sharpness of the curve. I maximum is equal to V by R. So just now we discussed very large value of resistance. Whatever the curve, this is the curve we will get. Flat end. The resonance frequencies, these are the resonance frequencies F0, and then this is a upper and lower cutoff frequencies of 980 and 1000. Fine. 1020. The same thing, what will happen, the resistance will be very small. This is the curve we will get. Okay, sharpness of the curve. That means that the sharpness of the curve is depending upon the resistance already we discussed. So the thing here, so sharpness of resonance curve, or the formula for sharpness of resonance curve, everyone note down this particular formula. Sharpness of resonance equivalent to F2 minus F1 divided by F0. Sharpness of resonance curve. That will be equivalent to change in frequency, that is a bandwidth divided by F0. So that is also divided by 1 by Q0. 1 by Q0. So these are the formulas related to the sharpness of the curve. Okay. Then we are moving to the tuning. So tuning is nothing but, in the radios and televisions, olden days, we are using that variable resistor, that is a tuner is using to tune the particular frequency. Here also same thing. For example, I can connect it to the frequency of V1 5 kilohertz. Okay. What about the frequency you will get? What about the frequency you will get in this particular V1 case? So the resistors and R and L and the capacitance we are maintaining to 40 microfarad. So 40 microfarad is a capacitor. What about the tuning frequency? The tuning frequency F0 is equal to 1 by 2 pi root LC. So can substitute all the values. 2 pi root, what is a L value? 2 25 microhenry 10 power minus 6 into what is the C value, 40 into 10 power minus 6, then you will get 5 kilohertz. For your understanding purpose I am deriving here. Again I selected the capacitor value. I selected the capacitor value 10 microfarad. Let us take the example. So in that particular case we are going to do that everything you will get 10 kilohertz. So what I am saying that whenever your capacitor's value is decreases, the what about the frequency increases. So now here the selected frequencies is depending upon the capacitor or not. That's why tuning of the circuit is doing based on the variable capacitance, the required value. So that particular effect we are going to discuss here. Tuning ratio. How the tuning ratio will be. Okay, we'll discuss now here. Tuning ratio means F naught is equal to 1 by 2 by root LC. Yes or no? That is a resonance curve. So in that particular case, F naught is directly proportional to 1 by root LC or not. That means that in this particular case, I can change the capacitor value double or 4 times. Capacitor value changes to 4 times in the previous case. Yes or no? I change it to capacitance value 40 to 10, 4 times. What about the frequency? Doubled. Okay, the frequency is doubled according to this relation. That is also important in the examination point of view. Tuning ratio concept. Okay, if your capacitor is changing to 4 times, what about the resonance frequency? Change it to twice. Okay, next we are moving to the ratio dialing. The ratio dialing, so in the radio tuning dial, whenever your capacitor is tuning from the particular value of capacitor is variable, then you will get some resonance frequency. For example, you are tuning to 92.7 FM. Okay, in that particular case I can adjust this capacitor value to the 92.7 FM, the 92.7 frequency, then I will get the particular frequency signal I am receiving that. So that is about the tuning. It can be used in radios and televisions, etc. In the olden days television, but now we are remote control is there. In the particular case olden radios also we are tuning with help of the capacitor dial. Okay, in that particular case we have capacitor ratios will be 3:1. Sometimes the ratio will be 9:1, like that. Okay, that is about the radio tuning. Then we are moving to the problems related to this particular RLC and then selectivity as well as F naught resonance frequency, all these conditions. Okay, let us discuss the first problem. RLC circuit consists of a capacitive reactance of 120 ohms. That means that XL is equal to capacity, XC is equal to 120 ohms, and having a resistance, that is R is equal to 60 ohms, and inductive reactance XL is equal to 180 ohms. Fine. The combination connected in series with frequencies of 50 Hz as well as voltage is of 200 volt. Fine. So now they are asking about the current, power factor, power taken from the circuit. So from power taken from the circuit. So for first of all, current I is equal to V by Z. V by Z. What is the V? 200. But you don't know the Z. So you can find out that Z is equal to square root of R square plus, XC is more or XL is more? XL is more. That's why XL minus XC whole square, the formula. So from that, square root of what is the R value? R value is a 60 whole square plus 180 minus 120 whole square. That value of impedance will be 60 ohms. Okay, 60 ohms. So inductor is dominating, that is inductive. That will be voltage is a 200 divided by 60. that will be equivalent to 2 amperes. Okay, uh, not 2 amperes exactly, sorry. Current will be equivalent to 2.36 amperes. So this is about current. Second, they are asking about the power factor. So power factor cos phi is equal to R by Z. You know that. What is the R value? 60. What is the Z value? 60. R value 60 and the Z value not 60, I'm sorry, 84.8 ohms. 84.8 ohms. So that will be 84.8 ohms. Okay, that will be equivalent to 0.707. It is inductive here, it's dominating, that is a lagging. So that point is also 1. After that, third point is a power. P is equal to VI cos phi. So from that, what is the voltage? 200. What is the current? 2.36. What is the power factor? 0.707. Then you will get the power is a 333 kilowatt. So that's what your explanation about the RLC circuit. But in the examination, they will ask either power factor, but the numerical values they mention in the, because calculator is not allowed, the ratios will be cancelled by the numerator and denominator. That particular values will be given in the examination. Don't worry. And then next we are moving to the question number 5. Okay, in this particular problem, a circuit consists of a capacitor C is equal to 100 picofarad. Pico is nothing but a 10 power minus 12. Is series with the coil resistance is equal to 5 ohms and inductance L is equal to 100 microhenry. They are asking about the first calculate the resonance frequency. Okay, you know the formula for resonance frequency. F naught is equal to 1 pi root LC. 1 pi root, what is L value? 100 into 10 power minus 6. C value 100 into 10 power minus 6. So that value will be 1.59 megahertz. That is the frequency of a resonance condition, resonance frequency. And then the second one, they are asking about the quality factor Q. Quality factor Q is equal to 2 pi F naught L divided by R. 2 pi F naught divided by R. Substitute that value. 2 pi F naught is the resonance frequency 1.59 and 10 power 6 megahertz, right? Into what about the L value? 100 into 10 power minus 6 divided by 5. That value will be 200. Okay, quality factor is a 200. Third point is a bandwidth. So the bandwidth formula. Bandwidth is equal to F naught divided by Q naught. Bandwidth F naught divided by Q naught. What is F naught? 1 pi into 59 into 10 power minus 6. Sorry, 10 power plus 6 divided by, what about the quality factor? 200. That will be 7.9 kilohertz. Kilohertz is a frequency. So this is about the bandwidth. Okay. Next we are moving to the parallel resonance. In the parallel resonance, what we discuss in the series resonance, the quite opposite to that. So at parallel resonance, capacitive susceptance, that is a BC, is equal to inductive susceptance. Both are equal, then you will get this particular condition, parallel resonance. So in the parallel resonance, the current value, so that is I is minimum. The current value is a minimum in the case of parallel resonance. After that, the frequency and current graph will be like that. Whenever current frequency is a minimum, whenever the resonance condition occur, what about the what about the f naught value? So what about the f naught? At the condition of f naught, current value is going to be minimum. When our current value is going to be minimum, what about the frequency is maximum? So this is a, in the case of parallel resonance, that is the case. So impedance diagram, this is the impedance. So at off power frequency is nothing but a 1 by root 2 times of Z maximum. You will get the off power frequency. The bandwidth will be upper cutoff frequency minus lower cutoff frequency, f2 minus f1. You will see one by one. F naught is equal to, the formula is same, 2 pi root LC. The formula is same for both parallel resonance and series resonance. We are neglecting some parameters. So next one, I minimum is equal to, because current will be minimum, V by L by CR. So L by CR is nothing but a Z. Z is a L by CR. So I don't want to do the complete derivation for you. So these two are connected in series and parallel with the XC. The combination will be the Z. Okay, L by CR. Clear? Next. So we just remember this particular thing, Z is a maximum here. That's why current is a minimum. So we have to discuss the few points related to that, the characteristics of the series parallel resonance circuit. It offers, you will see, it offers minimum impedance. It offers minimum impedance. The second point you need to remember, maximum impedance. Z maximum impedance. It offers minimum current. Minimum current. But since resistance almost negligible, practically DC drop, that's why in this case also cos phi power factor is unity. In case of parallel resonance also, the power factor going to be unity. So quality factor Q is equal to 2 pi f naught L by R. That is a formula for quality factor. We have to remember. After that, bandwidth. Bandwidth is nothing but a delta F, that is a F2 minus F1, that will be equivalent to F naught by Q naught. Okay, these are the things we have to remember in the parallel resonance. Is it okay for you? Then we are going to discuss one problem on parallel resonance, then we will end up this particular chapter. So the problem here, a parallel circuit consists of a capacitance value is given, C is equal to 200 picofarad, and inductive 200 microfarad. Resistance R is equal to 5 ohms. Connected across the voltage is equal to 0.2 volt. The frequency is equal to 800 kilohertz is a signal. They are asking about the resonance frequency. The first point here, resonance frequency, that is F naught. F naught is equal to 0.159 by root LC, that formula you know that. So 0.159 divided by root L, 200 micro into C is a 200 pico. That will be equivalent to 800. So next 800 kilohertz. Next one is the quality factor, Q value. So quality factor Q is equal to, Q naught is equal to quality factor 2 pi F naught into L by R. Already gave that formula. So 2 pi 800, that is a kilohertz, 10 power 3. L value is at 200 into 10 power minus 6 divided by resistance is a 5. You will get quality factor will be 200. Okay. Then third one is a impedance. So impedance is a maximum in this case. That value will be L by CR. So what is it? L 200 into 10 power minus 6, C 200, and R 10 power minus 12 into 5, that is equal to 2000 ohms. So after that, C, I minimum is equal to V by Z maximum. So what is the voltage? 0.2 by what is the Z maximum? 2000. So that is a 1 microampere. At the last bandwidth they are asking. Bandwidth is equal to F naught divided by Q naught. What is F naught? 800. Q naught is 200. You will get 4 kilohertz. So for your understanding purpose, how to use these particular formulas, I explained this particular problem. With that, we completed the chapter number 2, that is a series circuit. Next, we are going to start the time constants, that is the chapter number 3. And then thank you.